Susan Rambo, Executive Editor at EE Times. Today is day 3 of our 3-part class on controlling brushless DC motors. Our focus today is field-oriented control. This series is brought to you by EE Times and our sponsors ST Microelectronics and Mouser Electronics. If you attended the last 2 classes, you know that our instructor is Adam Reynolds. Adam is a solutions architect at Line Stream Technologies, where he develops new motor control and motion control projects. Welcome back, Adam.
Thanks, Susan.
Just some housekeeping. Adam will speak for 45 minutes or so. Post your questions during the class in the question box for Adam to answer after his presentation. We will hold the webinar open as long as we can to answer your questions. Rest assured, all your questions from all 3 classes will go into a Q&A that we will email to registrants and post in the archive with your names and company information removed to protect your privacy. You can download the slides now from the green Resources List widget on your audience console at the bottom of your screen. The slides will also be available in the archive. Early next week, we will send an email out to all registrants with a link to the archive. As part of its sponsorship of this great class on BLDC motors, ST is giving away up to 100 STM32 Nucleo motor control pack kits to registrants who filled in the optional field describing an innovative application they might use the kit on. After the course, ST will have a panel of its engineers and marketers select the 100 most innovative entries, and Mouser will ship the kits to the winners 1 to 2 weeks after the completion of the course. Today, we also have 2 engineers from ST, Giovanni Tomasello and Chung Peng, on the line to help answer any questions you have about STM32 and the motor control pack. If you have specific questions about the STM32, please address your questions to our ST engineers. You may also get answers individually via the chat from our engineers during the talk. Welcome, Giovanni Tomasello and Cheng Peng.
Good morning to everyone.
Good morning, everyone. This is Cheng Peng.
Thank you. Okay, get ready to learn about field-oriented control of BLDC motors. Take it away, Adam.
Thanks, Susan. And so, as you mentioned, today we're going to focus our discussion around field-oriented control for brushless DC motors, which is the more complex of the 2 control techniques that we discussed in class number 1. So let's have a brief refresher over the operating principles of this motor that we're going to talk about today. So brushless DC motors are made up of 3 phases, the U phase, the V phase, and the W phase. And each of these are spaced 120 degrees apart. And so by pushing current in through the motor phases, we're generating a magnetic field inside the motor. And that's called the stator magnetic field. And that's the pink arrow here on the screen. Now this pink arrow is going to interact with the permanent magnetic field that's generated inside the motor's rotor. That's the red arrow on the screen. And so what happens is that we create the magnetic field in the stator such that it pulls the rotor's magnetic field into alignment. So that's what creates the torque inside of an electric motor. The analogy I always use, and I've talked about it a couple times during the class, is with a donkey and a carrot. So I like to think about the B stator as the carrot. It's attracting the B rotor, that's the donkey. That's what's doing the work for us. So today, field-oriented control is based on what's called sinusoidal control. And so in sinusoidal control, one of the key differences from trapezoidal or 6-step that we talked about yesterday is that instead of only exciting 2 of the 3 motor phases, we're going to excite all 3 of the motor phases. So what this is going to do is it's going to allow us to position B stator in any location around the motor. So as you can remember from trapezoidal 6-step, we can only place that stator magnetic field in 6 discrete locations. But now with sinusoidal control, we can place it at any location. And so the position we're going to choose to place that magnetic field is always going to be 90 degrees with respect to the position of the rotor's magnetic field. And so the reason we do that is because that's the position that's going to allow us to produce the maximum amount of torque out of our motor. So imagine you're turning a wrench. You want to turn a wrench pushing 90 degrees with respect to the angle of the wrench, because again, that's where you get the maximum torque. And the same principle applies here. In order to produce the maximum torque out of the motor, we want to be pushing 90 degrees relative to that axis. And so in order to do that, to be able to place our B stator in the right location, it's going to require us to know the position of B rotor. And so that's one of the topics we're going to talk about more and more throughout this presentation, this class, is how do you either use an existing sensor on the motor or use the motor itself to tell you the position and the location of B rotor, because it's very important in sinusoidal control. So what we're trying to accomplish here is trying to use sine waves to accurately control this and generate a rotating magnetic field in this machine. And so how do we actually even do this? And that's where the control technique called field-oriented control comes in. So to give a brief overview and description of field-oriented control, its entire goal is to simplify the torque control of the motor and to make it very similar to controlling a DC motor. So the first thing we're going to do is we're going to measure the currents flowing through the motor. And so that's this line that's labeled IU, IV, IW, going into the Clark transform. That's the measured currents that are flowing through the motor right now. Then we're going to compare those measured currents against the desired current. So we have the IQ and the ID going into summing junctions with the feedback currents. And then we're going to take that air signal and amplify it in order to create a correction voltage. Because since we can only control the voltage that's applied across our motor, we have to monitor the current and then adjust the amount of voltage such that the motor is producing the right amount of current. And so we're then going to modulate that correction voltage out onto the motor terminals. So that's essentially what this block diagram is doing. But there's a little bit of complex math going on here. So in order to, let's follow the path around and kind of talk through the different blocks of field-oriented control. So what the measured currents actually represent is the magnitude and angle of the current in the motor. And this is aligned with that stator magnetic field. So what the Clark transform does is it converts the 3 vectors into 2 vectors. And that's because the sum of any 3 vectors can obviously be represented by 2 vectors. And this is really done to simplify everything else. And then the Park transform, what its job is to take the now 2 vector rotating or stationary frame that's in that still in AC, still sine waves, and convert it into DC by removing the angular component. And so what that's going to do is it's converting from what we call the stationary reference frame, or the reference frame of the stator, onto the rotating reference frame. So it removes the angular component from these signals and converts our sine waves into DC values, which is going to make it very easy for us to operate on them when we go up here to the PI controllers. So the output of this Park transform, there's 2 vectors. There's the D vector, which is called the direct vector, and that's aligned with the rotor magnetic angle. So that vector is exactly equal to wherever the position of the motor rotor is, as represented by the theta here in the diagram. And then the quadrature vector is always placed 90 degrees from the direct vector. So this way it's quadrature, it's 90 degrees relative to that vector. And so what these represent actual real values in our motor. And so the direct axis, or the direct vector, is also called the flux vector. So it represents the amount of current that's either helping or detracting from the magnetics in the motor. And since our permanent magnet motor has all the magnetics it would need, we don't really need to do any additional current there. So we typically, for most applications, this ID value, the desired value, is always set to 0. Now the quadrature vector, that's the torque-producing vector of the motor. And so the output of your speed controller, which is telling your motor to either apply more torque or less torque, is the input to the desired Q-axis vector. And so this way, we can use our speed controller to tell us whether or not we need to accelerate or decelerate the motor in order to meet the speed objective. And so we use PI controllers in order to take that error signal, that difference between the desired amount of current or torque and what we're actually measuring in the system. And we use them to amplify that signal and transform it into a voltage, because that's, again, since we are using switches in order to adjust the voltage on the motor, we really don't directly say more current or less current. We say apply more voltage or less voltage such that we get more current or less current. Because the motor is effectively just a giant filter. It's taking that modulation, that voltage, and then we're looking at the current that we're generating in that system. And then we go, after the output of the PI controllers, we go into what we call the inverse park block. So this re-adds the angular component that we took out from the previous part transform. So it takes us from this rotating reference frame back out to the stationary reference frame. So it tells us, how do we apply the voltage that we want to be applied to the rotor out on the stator? And then the space vector block, or the space vector PWM block, converts this command voltage into duty cycles that we need to apply out onto the motor terminals. Now this is a very kind of rough overview of field-oriented control. Obviously there's a lot of different tricks and a lot of different things that can be done and modified in order to make this either more efficient or it's more directly tailored in for your specific application. But this is a basic overview of kind of how it works. What's the objective of this control technique? And so now it's not necessarily critical to understand it completely thoroughly, but to be more aware of how it operates and what it's trying to do. Because there's a lot of software packages out there that are really designed to make this process easier, because it's a very well understood process. So what implements this control technique? And obviously we're going to be doing this on a microcontroller. So the microcontroller is what realizes this control algorithm. And so it's commonly done via periodic interrupt. And so typically you'll set your interrupt up so that it will interrupt every time the PWMs need to be updated. So the microcontroller's job is to handle all of the timing and the synchronization of all these motor signals. And it's typically using integrated pulse width modulation hardware on the microcontroller. It also reads the feedback. So in this case, we're reading the motor phase current. We're using the analog to digital converters of the microcontroller to read back how much current is flowing through our motor. And we're also reading an encoder, which could be many different interfaces. It could be quadrature, it could be a SPI interface, it could even be an analog interface. But we're reading that we need to know that motor angle feedback in order to get the rotor position in order to do all the field-oriented control. And of course, later on in this presentation, we're going to talk about sensorless control, where we don't need to read the feedback from the encoder. So the microcontroller really is what implements this field-oriented control algorithm. It implements all this math in order to simplify the control of our motor and make it so we can control based on those DC values of IQ or torque and ID or flux. So the relative timing of things inside the microcontroller is very important. That's why using a periodic interrupt with field-oriented control is actually more important than it is with trapezoidal, because we need to time out when certain events happen, and they need to happen at a specific timing relative to each other. So let's look at the requirements for implementing field-oriented control on a microcontroller. So it does require a bigger MCU than trapezoidal or six-step control. So obviously in the censored implementation, it takes on the order of 20 plus MIPS. And then with sensorless, obviously it takes more because there's additional math going on. We need to do math on those feedback currents in order to estimate the rotor position, which it just takes a lot more processing. And then in terms of peripherals, it needs obviously pulse width modulation in order to modulate the voltage out onto the motor terminals, which it doesn't need much better pulse width modulation than what the trapezoidal or six-step control did. It can use very similar peripherals. But the analog to digital converter does need to be a bit better. It needs to have ideally better resolution. Typically 12 bits is pretty good, 16 bits is obviously better, but 12 is usually acceptable. And then anything above about 600 kilosamples per second, because you need to be able to sample the currents flowing through the motor fairly quickly. And obviously whatever encoder you're using in your application, that's going to determine the interface you need. So like I mentioned earlier, it could be quadrature, it could be SPI, it could be PWM, could even be a resolver inputs, which requires a whole different set of hardware. So there could be there's a lot of different encoders out there, and each of them requires their own interface. So you're going to need to figure out what's required for your application specifically. So let's take a look at the hardware we're going to use, or just a brief overview of the hardware that we're going to use to control this motor. So you notice from the class yesterday that the MCU, the gate drive, and the PWM components are all the same. They can use very similar, if not the same components that are used with trapezoidal or six-step control. It's really effectively the same circuit. The big difference is that we need to be measuring the phase current feedback. So as you can see on the diagram, we have feedback sensors on all three of our motor phases. And this is because we need to control, we're directly controlling the current in order to orient the magnetic field inside this motor. So in order to do that, we have to have very accurate measuring of the phase current of the motor. And then of course, if you're using a sensor, you also need to have the encoder angle feedback also returned to your MCU. And what we said yesterday when we were discussing trapezoidal or six-step control, these sensors are really the least robust part of the system. And so in FOC control, that's even more critical. Encoders are notoriously much more fragile than even Hall effect sensors. And so it adds additional connectors, additional power supplies. It adds a lot of complexity and risk into systems. And so that's why there's a lot of sensor work in the sensorless algorithms to be able to remove this dependence, because it can make it very difficult to have a high degree of robustness on your system. Now obviously you can buy better and better encoder hardware, which will improve your robustness, but at that point it's also additional cost. And if you can do a sensorless algorithm based on the motor phase currents, which you're already measuring anyway, that adds a lot of robustness into your system. So let's look in more detail at the current sensing hardware. So this is what actually is on the circuit board in order to detect those motor phase currents. So the most common way of doing this is with inline resistors. So the diagram, the circuit I have here on the on the right, it has the V-bus, which is our DC power that's coming in to power our motor. We have two switches. We have a high switch and a low switch, with the motor phase connected in between. And then we have the sense resistor between the low switch and the ground. So one thing that's important to note about this circuit is that you can only measure the current flowing through the sense resistor when the low switch is actually closed, because you want current flowing from the motor phase through the low switch, through the sense resistor, into ground. So that's the only condition when that is true. So that what this means is that the measurement needs to be timed correctly. So you have to make sure that you're triggering your analog to digital converter measurement such that it's happening when the PWM module indicates that the lower switch is going to be closed. And so most of the microcontrollers that are directly targeting motor control applications have the logic required in order to do this. They'll make sure you can set it up so that way it'll trigger an ADC automatically based on when the hardware pulse width modulation module says the low side switch will be closed. So that's something you don't necessarily need to worry about with most microcontrollers. So the way that this sensing hardware works, once we have been able to make sure we're getting the measurement at the right time, is that we're looking at the voltage drop across the sense resistor, and then we're going to amplify it. So you're typically connecting a non-inverting difference amplifier up to that voltage drop, and then that's going to determine the ratio between how much current is flowing across the resistor into the scaling that feeds into your MCU. And so obviously it's important when you design your hardware to make sure that you're covering the entire range that your motor is going to see in terms of current with respect to the range that's ratable by your MCU. But one thing that's important to consider and keep in mind about field-oriented control and being able to sense the phase current is you actually don't need to sense the phase current in all three phases. It isn't required. It will give you the best performance, but it's not required in all applications. And the reason you don't need to do that is because the sum of the three phase currents is 0 based on Kirchhoff's voltage law. Kirchhoff's current law. I said that wrong yesterday too. So what that means is that you can calculate the third current based on the other two, since you know that the sum of them is always equal to 0. However, doing this will limit the top tier performance. And that's because as we discussed, we can only do the measurement when this low side switch is closed. And since your ADC does not read immediately, it does take some amount of time in order to actually capture a reading. So what happens in the situation when you're trying to drive maximum power through your motor? You're going to be leaving the high side switch on for as long as possible, and the low side switch is going to be off for as little amount of time, on for as little amount of time as possible, which means you may not have enough time where the low side switch is on, such that you can even do an ADC reading of the current. But fortunately, this will never happen on all three phases at any one time. Since the three motor phases are separated by 120 degrees, the peaks of those sine waves will never be aligned. And so based on the knowledge we have that the circuit is balanced, you can always reconstruct your third current from your other two currents. But that assumes that you have all three currents and you know which one is going to be peaking at any one time, so you can make sure you're not ignoring readings from that particular current sensor. So this is more of a complex issue that you run into with FOC, but it's something to keep aware of, that if you don't require the absolute top performance that you could possibly get out of your motor, it's something to consider that can save quite a bit of cost in your application. Now obviously this is only one example of how to do current sensing. You can do a lot of other things such as inline Hall effect sensors, and there's many other techniques of doing this, but this is just the most common example. So before we talk about how the sensorless algorithms work for field-oriented control, let's talk about the electrical model of the motor. Now this is something that we're going to base the sensorless algorithm on, so it is quite important to understand. So the first thing we're going to look at here is this is our motor. It's got our three phases, U, V, and W. And we're going to model an impedance and our back EMF source. And our motor obviously has a center point, so they're all connected in the middle. So this impedance is the combination of the phase resistance and the phase inductance. Now for most of the analysis around basic sensorless, you can ignore the inductance. It does come into play, but for simplified sensorless control, you can ignore it. And then we also have our back EMF, our back electromotive force generators. This is that back EMF force we talked a little bit about yesterday. So this is the model of the three sine wave voltages that are delayed from each other by 120 degrees. Now what's important to know about these is that their amplitude is directly proportional to the speed. So the faster you're going, the more back EMF there is in your system. And so that's really important for sensorless control. And really all sensorless algorithms are based around about this knowledge, about how the motor works electrically and its basic components. So if we look at sensorless estimation, each rotor location has a unique back EMF when you combine the three motor phases. So what this means is that we can estimate the rotor position based on that back EMF. So in order to estimate the back EMF in our generator here, we have to know a couple things. We have to know how much voltage we are applying to each of these phases. And we can do that based on the PWM duty that we know about, that we've tried to apply. That's a known number. We can convert that into how much voltage we should expect for that phase. We need to know the motor phase current, which we're already measuring because we have to control the current, so we need to be able to know the current to control it, so we're measuring that. The other one we need is the motor model parameters. So we need to know the stator resistance. We need to know how much voltage are we losing across this resistor. Because effectively, that back EMF, it actually tries to counteract the voltage we're applying to this phase. So the more voltage we apply to the phase, let me restate that. The faster we try and spin the motor, the more voltage we need to apply to that phase in order to overcome this back EMF, because this is resisting our rotation. So by taking out the voltage drop across this resistor, we now know how much voltage we're actually generated by back EMF, because that's just the voltage we applied to it minus whatever voltage it took to overcome the current flowing through that resistor. So this is just a basic example of how to get that back EMF. And then once we have it, what do we do with it? So by taking in the back EMF estimates that we've calculated based on our knowledge of the circuit electrically, we can, obviously since it's three vectors, we can represent it as two vectors, and then we can take the arctangent of those two vectors to figure out the angle of the motor. And so this is just one example of a fairly simple senseless algorithm, and it's just the basis for a lot of different senseless algorithms out there. Now obviously, since this is a simple example, they only get more and more complex and more involved, and can consider a lot of other models and a lot of other things in your circuit that will improve this model. So let's talk about some of the considerations for sensorless control. So obviously, since we're doing the sensorless based on the back EMF, we have to have the back EMF in order to estimate that angle. And since the back EMF is proportional to speed, that means that the sensorless is just not going to work well at low speeds. So the typical rule of thumb is about 10% of rated speed is where sensorless starts to begin working very well. Much below that, it's difficult to separate signal from noise. And so you tend to have sensorless estimators that don't work really well much below 10% rated speed, just because there's a lot of noise in the signal. And so back EMF is really ultimately based on motor phase current. So if we go back and look at our sensorless algorithm that we talked through, we really need to know the phase current, because that's going to determine how much loss we get through this resistor. How much voltage drop through this resistor based on the amount of voltage we're applying. So we have to know that current pretty well in order to do a good sensorless estimation, because that's the only thing that's actually measured. Everything else we either know from the motor data sheet because of the stator resistance, or we know because we commanded it, so we know exactly what the phase voltage is because that's what we're applying to the motor. And so what this means is that in order to do a really good back EMF estimation of your motor, you have to have good sensing hardware. And so part of that is you need to make sure that your sensing hardware is actually scaled correctly. For example, if the peak current on your motor is only 5 amps, you don't want to set up your sensing hardware to sense a total of 20 amps. Because what will happen is throughout most operation of your system, you're only using the lower quarter of the bit of the resolution available to you. So that's a ton of resolution you're throwing away and not making use of. And so what that's going to do is it's going to degrade how good your field-oriented control performance can possibly be, because you don't have as much resolution as you really could use or really could have in your application. And so being able to balance the range of resolution with the maximum peak current you're ever going to see is really an important thing to consider. And so it can be a little tricky to make sure that you're leaving enough headroom, so that way if you have a situation where you need to drive a bit more current than the motor rated, but you can still sense it and you're leaving yourself enough room so that way you have good resolution. It can be tricky to balance. And one of the things that often happens is that there's a lot of proprietary algorithms out here that are provided often by MCU manufacturers who have spent research and be able to differentiate their product by having a unique offering in the sensorless space. So we've talked a little bit about sensorless when you're actually running. But we have some of the same considerations we talked about yesterday with trapezoidal 6-step with actually doing the startup of the motor when you're doing sensorless. So when there is no back EMF to sense, how do you actually get the motor to begin rotating? So if I jump back to our motor diagram, we can talk about how the sensorless startup works, just as an example of one of many different implementations. So what we can do when sensorless startup, and this technique is really called an align and go technique, is we can impose a specific orientation of the field of the stator on the motor for a brief amount of time. So in this example, let's imagine we are picking our stator field to be exactly where this pink arrow is. So what's going to happen is if we don't rotate that angle, if we hold our motor in this position, the rotor is going to rotate such that those magnetic fields are aligned, because that's what it wants to do. And so then at that point, we can begin manually advancing this rotor field. We can begin rotating our stator field such that we're always trying to keep the stator field and the rotor field perfectly aligned. So we're not yet doing quadrature 90-degree control. We're purposefully trying to keep that difference degree, that angular difference to be as small as possible. So this way we're just trying to rotate it along with us until we spin fast enough such that there's enough back EMF for us to actually estimate that rotor position. So this technique, it works pretty well, and it's a fairly common technique, but some of the problems is that you often need quite a bit of current to apply to your motor in order to actually get it rotating. And that's going to be dependent on how much inertia there actually is on your system. So obviously motors that have bigger inertia and more mass they're trying to turn, this technique is going to be very difficult because you're going to have to apply a lot of current in order to drag the rotor into alignment and then to drag it around with you and accelerate it up. It's also highly dependent on the rate of acceleration. So that kind of works in concert with the inertia. Obviously, the faster you're trying to accelerate, the more current you have to use in order to keep your motor rotating. And so that can be something that's kind of tricky to balance. One of the advanced techniques that's available, that's in the market, is what's called high-frequency injection or initial position detection. So what that does is it actually injects high-frequency sinusoids into the phases of the stator. And what that'll do is it will look at the feedback currents based on that high-frequency injection and be able to figure out the relative angle of that rotor. And this is a very advanced technique that can be tricky to tune and tricky to adjust, but it can allow you to start very, very quickly and not have to suffer as many of the penalties with that sensorless startup that we talked about. Now you can also do a lot of other things. You can even integrate Hall sensors into sensorless for your startup considerations. By using the Hall sensor, you can know kind of an initial guess as to where the motor is. And then from there, you can choose that as your seed angle. Because what we do when we talked about align and go is that we're just picking an angle. It can be completely arbitrary. So worst case, your motor is perfectly 180 degrees away from it. So that's your absolute worst case. So that means the motor has to rotate all the way around to 180 degrees before it can actually start working correctly. Now what if we had our Hall effect sensors and we could cut that down to within 60 degrees? So that's a much better situation to be in terms of this align and go technique. So having those Hall effect sensors can be useful in FOC control as kind of a sanity check in terms of when you're doing this startup. So you just use them to start up and then you can keep running from there. And so it actually also helps eliminate some of the robustness issues you run into with Hall effect sensors, in that the application would still work if those Hall effect sensors didn't exist. They'll just work better if they're there. So again, this is one of these things that can be a difficult application area when working with sensorless FOC and does require a bit of expertise, but it's something that is a solvable problem, and it's something there's a lot of different ways to solve this issue. So if we look at a real-world example, obviously the ST's motor control Nucleo pack is a great application to be able to is a great kit to be able to begin building your application. It's based on top of the 72 megahertz ARM Cortex-M4 microcontroller. So this is a microcontroller that has plenty of MIPS to be able to run your sensorless FOC control plus a bunch of your application code. So this way, it helps you save time in your design by being able to combine things into a single microcontroller and not have to have a dedicated motor control microcontroller. It's based on the L6230 motor driver. It has a pretty wide voltage range of operation, and is compatible with the ST FOC, when both sensored and sensorless. So if we go take a look at some of the motor control firmware available from ST, it's really a complete software package that features simple APIs, a PC GUI, and it's portable across all the different ST MCUs. And this does implement field-oriented control, both sensored and sensorless. It also includes some advanced functionality, such as the HFI, the high frequency injection initial position detection that we talked about earlier. It also features MTPA, which is designed for interior permanent magnet motors that have some special considerations. And it also features field weakening, which allows you to run the motor at much greater than rated speed. And that's an advanced use case that's really helpful in like washing machine applications, for example. And it has pretty good documentation that covers all of the material we've talked about today and much more. It's really a good theoretical reference in addition to the information about the SDK, because while I've scratched the surface in terms of field-oriented control and kind of giving an overview of it, having that theoretical reference when you're actually designing your application can be really important to help understand what your motor is doing and why it's doing what it's doing, and how can you, as the application developer, go and modify the FOC, or what parameters do you need to adjust in order to make it work correctly for you. So having the good theoretical reference really is important. So Susan, I think we've reached the end of my presentation. I think we're ready to open it up for questions.
Okay, great. Great, Adam. That was wonderful. Let's see what questions we have. Don't forget to continue putting your questions into the question box. We will answer as many as we can. Okay, here's one from Narendra. If motor impedance is not balanced, how will it affect motor performance?
Well, it's gonna cause problems, because that's kind of the basis of a lot of the thinking around FOC, is that it is balanced. So what will happen is the waveforms of current that if you were to hook up a current probe off an oscilloscope to look at would no longer be identical, and so it would cause some rather strange effects, and it's really not typical unless you have a problem with your motor.
Okay, here's another one. Is it possible to find the impedance imbalance of the motor?
There are some. I mean, since impedance imbalance really isn't a common occurrence, what you really tend to think about more is like lost phase detection. So if you have a motor phase that is suddenly disconnected, that's a much more common occurrence, and so most of the detection is really around that. And so you can look at the feedback currents and look at your applied voltage, and because you know the motor parameters, you know that state of resistance, you have an expectation of roughly what the current flowing through that phase should be if I apply a voltage. And so if you're missing that current, or that current is wildly inaccurate, that can kind of give you a hint that something is wrong with your motor. It could be a disconnected phase, could even be an extreme imbalance. So you can kind of use some of these things that we know about the system by understanding the motor electrically in order to do that kind of detection.
Okay, here's one from Sagid. Using the carrot donkey analogy, can this control be configured to push the rotor as opposed to pulling it? If so, what is the difference in performance?
Yeah, using the same, if we apply that analogy, you can of course do that. So it's just really more of a sign convention than anything. So instead of we're thinking positive torque leading that carrot, leading the donkey, so to speak, and pulling it around, but if you were to apply negative current and then change your sign, change your angle, that's going to push it. So you can think of it either way. It's all about the direction and the sign convention you're choosing to use.
Okay, here's one from Michael. If the B rotor is 180 out of phase with the B stator at startup, will the alignment actually happen?
So if you're 180 degrees out of phase, your rotor will be attracted to the stator's magnetic field. It's just that it may not work very well. It depends on if you have an amount of time that you're holding that stationary magnetic field to try and get the rotor to align. So it's like a little bit like we talked about yesterday with the align and go technique. If you hold that startup for a fixed amount of time, it'll attract it around. But if you start at an angle and then just start advancing, you may not be able to attract the rotor and be able to catch it and be able to get it spinning. Now, obviously, there's very dependent on the application. For example, if you have a lot of inertia on your application, that can be more and more difficult. And if you don't use a lot of current to try and do that startup, it can also be more and more difficult. So to answer your question, yes, it will happen, but that's really the absolute worst case for it to happen in.
Okay, here's one from Tejas. Since it takes 2 PMW cycles for SVPMW to generate the desired voltage, shouldn't the control loop be at least half or lower than half of the PMW frequency? I understand there are other considerations, as you stated earlier.
It really depends on your application space. I've worked with applications that have done it both ways, and it really is kind of highly dependent on some of the other considerations, to be honest. But I've found that most of the time you'll tend to run it one-to-one in terms of PWM cycle update to FOC update, even though it does take those 2 cycles, but it still ends up controlling it pretty well, because especially if you're running that sensorless estimator, it's nice to have that extra information you're pulling in to be able to look at to be able to calculate that angle and get a good estimation for it.
Okay, here's one from Sunny. Does FOC handle a sudden step torque demand well?
Yeah, that's exactly what FOC is designed to do. So we touched a little bit about what exists above the field-oriented control, and that's a speed controller. So what will happen in your system, if you suddenly are on a dynamometer, for example, and you apply a step load and torque, you're going to see the speed start to dip. And so your speed controller is going to ramp up the torque that it's demanding. And so as soon as it does that, your current controller is going to say, well, I need more. I am not applying enough torque to the motor. My speed controller is demanding more torque, so therefore let me apply more voltage in order to produce more torque. And so since we're running this control loop at somewhere in the neighborhood of 10 kHz for the FOC and about 1 kHz for the speed controller, it happens very, very quickly, and it's designed to reject those type of load disturbances.
Okay, here's one from Zohaib. Why does the BLDC motor driver have single sense for the 2 phases and the third phase has separate current sense? Also, is it capable of sensing bidirection current through the motor windings?
So it's a good question. It could be based on a couple different things. So in terms of your question, it sounds like it's about a very specifically direct kit. But what tends to be most common is having 2 phase current sensors and doing the reconstruction on the third. Obviously, for applications that require much more high dynamic performance, they have all 3 current phase sensors. But there's also algorithms out there that can even just use a single sense resistor, and that's a much more advanced algorithm for doing this kind of FOC and sensorless control. So what we really talked about today scratches the surface, but there's other advanced algorithms out there that are really designed to help remove the reliance on some of those hardware pieces.
Okay, here's one from Jose. About the current sensing hardware, I am assuming it is a half-bridge driver. The sense resistor on the low side is a high impedance, 10 kiloohms, resistor, and the voltage is the one read on by the ADC to determine current flow.
So that's a good question. The sensor, right. So that's kind of what I talked about is that what we're really looking at is we're looking at the voltage drop across that resistor. Since we know what that resistor is, we can make an op-amp circuit that'll amplify that difference in voltage. It'll amplify it such that we can directly translate it into a current when we read the output of that amplifier. And so it really is it's typically a non-inverting difference amplifier that's used in order to convert the current flowing through that sense resistor into an ADC voltage. So it's not shown on this diagram because it's a well-known op-amp circuit. I just wanted to give a highlight as to what the hardware tends to look like and some of the considerations on when you can actually do the sensing of that motor phase current.
Yeah, I can add maybe 2 more cents on top of that.
Okay, go ahead.
Yeah, actually, Adam said, is absolutely correct. Usually, we use shunt register for the current sensing, and the size of shunt register usually is very small, and it's usually less than 100 milliohm, or even something is 20 milliohm, 25. And then the one thing in the hardware design, you need to make sure because the op-amp will sense and then the ADC op-amp, and then eventually it sensed what is dropping on top of the shunt registers. You want to avoid the saturation. It means if you select a very big register when current going through, and then you're going to saturate your, the op-amp, which is not good. And the second, the current that goes through shunt translates to the heat. So you don't want a lot of heat dissipation of the board. So typically the shunt register is a very small value. That's it.
Thank you. Here's one from Mark. It's a pretty general question. What are the biggest drawbacks of sensorless versus censored?
That's actually a really good question. So can be quite a few drawbacks of sensorless over censored control. But again, it really is based on your application requirements. So, for example, in sensorless control, if you need to control below about 10% of rated speed, you really can't do it. It's really extremely difficult. And so you really need a sensor in order to do that very well. And so similarly, that means that if you want to then not control the speed, but actually control the position of your motor, doing that sensorlessly is impossible. You really need a sensor to be able to control the position of your motor. That's because you're taking another control loop out beyond the speed loop. And so all of your air starts to accumulate, you amplify a lot more noise, and it becomes a very, very difficult problem. So those are kind of the two biggest drawbacks, is that low speed range and no position control of choosing sensorless. And then obviously the biggest drawback of censored is you have a sensor. It can be costly from a layout perspective because now you have additional power supplies you may need, additional wires, additional connectors, and it's also a system robustness problem because now that's the part of your system that's most likely to fail, and if it does fail, causes a lot of problems because now your motor just won't work. So there are some applications out there that actually choose to do both. They choose to run a sensorless observer and a sensor. So this way they have a fallback should the sensor fail, and they can safely drive the motor down to a 0 speed and alert an error rather than just giving up on the control because it doesn't know where the motor is.
All right, here's one from Enrique. If we want to limit the torque, would you limit the quadrature current at PI loop?
Enrique, that's exactly right. So what you would do is you would limit the output of your speed regulator. So what FOC is designed to do, it's designed to make torque directly proportional to current. And so by limiting the output of the speed regulator to an amount of torque or current, that's going to limit the maximum current you're applying in your system. So this is how you would do it, is you would limit it at the output of the speed regulator before it enters the PI controller.
Okay, here's one from Mark again. Is there better system for performance with an encoder versus sensorless? Also, how about how popular or how much is the censored versus the sensorless used?
Good question. So the system performance will be better with an encoder. If you're doing a speed control system, it'll regulate the speed of that system much, much more tightly with an encoder. And that's because you have much finer resolution. There's no filtering delays. There's no processing delays or a lot of noise that's entering your calculations. So you can get very, very accurate speed control. With sensorless, there can be you often have filters and you often have a lot of mathematical processing that happens on those phase currents as they come back in. And so it can cause delays, and the system can be a bit more sluggish than it would be with an encoder. And then in terms of popularity, it really is application dependent. For example, the vast majority of washing machines, for example, are sensorless applications instead of censored applications. But I've yet to go into a factory and see a sensorless control being used on a pick-and-place robot, for example, or even the vast majority of conveying systems are censored. So it's really application-focused, but it's becoming more and more popular as a control technique as a lot of these algorithms that are being provided and licensed are getting better and better.
Okay, here's one from Tom. During the PMW drive to the 3 phases, where there will be electrical noise injected in the voltage on the phase sensing resistors, is there a way to time the measurement of the current reading to the middle of the PMW in the ST part? So I think it'd be a great question for the ST guys, yeah. Yeah. Giovanni or Chong? Are you guys there?
Yes, sorry, I was on mute.
That's okay. Do you know which question I'm reading?
No. Can you please repeat it to me?
Sure. It's the one by Tom, and it's during the PMW drive to the 3 phases, there will be electrical noise injected on the voltage in the phase sensing resistors. Is there a way to time the measurement of the current reading to the middle of the PMW in the ST part?
Yes, absolutely, but that is not in the ST part, that is in the ST software. So you just time the reading of the current, adding a delay inside the software, and that's done usually to avoid reading the noise of the commutation.
Thank you. Okay, here's one from Sunny. What is the future after FOC?
It's a great question. So I don't really necessarily know if there is much of a future beyond field-oriented control. Where I see the key things coming is more advancements in sensorless techniques and more advancements in some of the different control modes we talked a little bit about during this presentation. For example, more advancements in some of the high-frequency injection techniques that allow you to do that initial position detection of the rotor. So this way you can bypass some of the problems you see with sensorless startup. And even improving the sensorless algorithm such that it can actually work at lower speeds than about 10%. And then even looking at some other techniques, there's also, we didn't really talk about field weakening, which allows you to run greater than rated speed. There can be some advancements there, especially when it's combined with the MTPA technology, which is targeting a very specific type of motors called interior permanent magnet motors. So I don't necessarily see the core algorithm as becoming out of date. Where I see all the advancements is all the supporting features around it.
Okay. Here's one from Fabian. I have a motor design with very low phase inductance. Is field-oriented control better than trapezoidal control? Are there any other techniques to cope with low phase inductance other than the adding external inductors?
You took my easy answer, but it's a great question. And I think from my experience that FOC can work really well with low inductance motors. And I've run FOC on about 10 microhenry motors all the time. And what it really depends on is the processing speed that you're running at and your PWM frequency. Because what you really want is you need the inductors in the motor to be inductors and not wires. So you need to switch them much quicker in order to get them to act like inductors. And so typically with like a low inductance motor, you need to be running your PWMs at on the order of like 20 kilohertz and above in order to even get them to act more like inductors. And so you also need to then run your current loop, your FOC loop, at least that fast. So this way you can be looking at the current very, very quickly and be able to respond extremely dynamically to the changes that are going to happen, because that's a very fast response system. So I think FOC is really well suited to those applications. It's just making sure that you're considering the fact that you have low inductance, and so you need to be able to run the FOC at a fast enough rate to make the motor act like a motor and not like just a wire.
Okay, here's one from Zoe. Is there any time when the current in the sensor resistors is reversed? What kind of filtering is recommended?
So Zoe, that's a great question. So the current actually will often be reversed, because if we look back at our diagram here of the sine waves, what we see is that it's both positive and negative for all three phases. And so about half the time, the current flowing through any phase is going to be negative. So the way that this is addressed is you'll bias your non-inverting difference amplifier that you're using to process that voltage drop across the sense resistor. And so you'll bias it to the midway point of your ADC, so you can measure both positive current and negative current. And then in terms of filtering, you don't really want a lot of filtering, because you want that signal to be very, very quick. And so the biggest filter you're going to need to worry about is the PWM noise. And so you can deal with noise at that level, but you'd still want to be able to have that current feedback extremely quickly. So that way you don't have to worry about, well, have I filtered away the fast dynamic response I need in order to meet my application objectives, while also filtering out any kind of noise from the PWM.
Okay, this is from Mihai. Can you tell us a bit more about the high-frequency injection method? It seems very useful. What is it based on? Does it have anything to do with asymmetry in saturation of the core?
That's actually exactly what it's based on. So what high-frequency injection does is it places the iron inside the core of the rotor, the magnets, into saturation. And so what you're trying to do is look at the subtle differences in the magnetics of the rotor for the D-axis and the Q-axis. And so what you're looking at is you're doing a high-frequency injection and looking for the subtle differences you see in how the rotor responds on those two different axes. And so it is based on not having perfectly symmetrical inductances inside the motor. So it assumes you have some amount of difference between your D-axis, what's called the D-axis inductance, and the Q-axis inductance. So I think one of the ST guys might be more familiar with their specific implementation of the algorithm, but that's kind of how it generically works.
Does anyone from ST want to take that? Maybe not. Okay. All right, we can go on to the next question, or maybe two more questions. We're already at the top of the hour here. So here's one from Tahir. What is normally the startup difference with censored or sensorless control?
So good question. So in censored control, there is never a startup period. They immediately begins rotating, because you always know exactly where that motor angle is. So even if you're not running the PWMs, you still know exactly what that angle is, because you're always measuring it. So in censored control, there is no startup period. It just starts. In sensorless control, that startup period will be, like I described, on anything below about 10% rated speed or so. And so that's really the difference, that in sensorless there is startup, and censored there isn't.
Okay.
This is Chang. I can add maybe 2 more cents on top of that.
Okay.
Yeah, like Adam mentioned, the startup is more like sometimes when the loop will be closed. right? When the position loop will be closed. When there is a Hall sensor output, we know the position at the very beginning, so we can close the position loop immediately. While in the sensorless, so like Adam mentioned, in a low speed, like less than 10% of full speed, so it's roughly the open loop. The loop will be closed at a higher speed. That's it.
Okay, thank you. Thank you, Cheng.
Sure.
I'm going to go back up the list to a question from Jeffrey. He asks, can interleaving the H-bridge inverter stages yield a smoother operation of the motor? If so, can it be implemented similarly to an interleaved power stage?
That's a good question. Unfortunately, I'm not as much of a power expert as the ST guy, so if I could have one of those guys jump in, that would be really helpful.
Giovanni or Cheng?
Yes, this is Giovanni. Actually, I'm trying to find the question because we have reading support.
This one is pretty closer to the top of the list. It's from Jeffrey, and I can read it again. It's from Jeffrey. It's, can interleaving the H-bridge inverter stages yield a smoother operation of the motor? If so, can it be implemented similarly to an interleaved power stage?
To be honest, I never thought about this option. Interleaving is very frequent when we talk about power conversion, like DC-DC or AC to DC, and that helps to reduce the power losses on the transistors and reduce the input ripple current. I'm not sure this would work with the motor because you always have these three phases. For a fork application with the BLDC, you always have three half bridges controlled in a certain way, and the purpose is to control speed and torque, not really to reduce the ripple current inside the wire of the motor. So my first guess would be that this is not something that you can implement to control the motor. But I might need to reach to Jeff directly because maybe his question has something more that I'm not understanding right now.
This is Cheng. I just want to second Giovanni's sort of comments. So if you think about it, the BLDC topology is always three-phase inverter, like a three-half bridge, UVW high-low side. And so we never saw anybody, like use just like the interleave things which widely, designed for the power industry.
Okay, thank you. Actually, let's do one more question and then we'll end it. Here's one from Asuk. Do we need to protect the input pins of the difference amplifier due to the voltage transients across the phase?
You'll usually have inline resistors just to help protect in the terms of circuitry, but it shouldn't impact the signal you're getting out of the voltage drop across that resistor, but you will tend to want to put resistors in there just to help protect it, the op amp.
Okay.
And you can find example circuits are available for the ST kit, and that's a great place to kind of pick up how to design this circuitry in such a way that it's beneficial. It works for your application.
Okay. Thank you very much. This concludes our three-part series on brushless DC motor control. I want to thank our instructor Adam Reynolds, our ST engineers Giovanni Tomasello and Cheng Peng, and our sponsors ST Microelectronics and Mouser Electronics. Most importantly, I want to thank all our listeners for your questions. These classes will be archived and available for viewing. We will also include your questions in the archive so you can read what other people were asking and the various answers we gave them. Watch your email box for more information about the class archive and the ST Dev Kit giveaway. I am Susan Rambo, and this has been E! Times University. Goodbye, everybody.